Bismillahirrahmanirrahim. Greetings. 2 days ago, from the date of this video, I uploaded a lecture about countable and uncountable sets. Now, in this video, I'm going to demonstrate a possible way of counting rational numbers. So let's start, shall we? Rational numbers are positive, negative, proper and improper fractions. Positive, negative, proper and improper fractions. Now, the integers are also among the rational numbers, because the definition of rational number is all the numbers that they can be represented as a over b, where a and b are integers. So for instance, 5 is same as 10 over 2. And so 5 is an improper fraction. So the set of rational numbers is all, again I'm repeating, positive, negative fractions and both proper and improper fractions. Now, the set of rational numbers, now if we select a unit length, which is arbitrary, and with respect to that unit length that we select, we can partition the entire number line into intervals. Now, the end point of each interval will be consecutive integers. Now, I have drawn a number line here. I partition that into intervals, and the length of each intervals are all same. And now, between any two consecutive integers, meaning in every interval, there are infinitely many rational numbers, infinitely many fractions. Now, the set of rational numbers is condensed, meaning between any two rational numbers, there is another rational number, simply the average of the two. And this process can go forever. So intuitively and common sense, we get the impression that the entire number line should only consist of rational numbers. No other numbers can be fit in there, because the rational numbers, they do not let them. Rational number always, between any two of them, there is another one, and keep going forever. Now I come back to this. Now, let me see. The rational numbers being infinitely many, and there is no order in the set of rational numbers. We cannot say what will be the next rational number. We can say in the set of integers, for example, 3, it has two neighbors, 4 and 2. But there is no such a thing in rational number. So in rational numbers, or repeat, there is no order. We cannot see what will be the next rational number. So if there are so many of them, infinitely many of them, and there is no order, then how in the world are we going to be able to count them? Interesting, isn't it? Interesting question. So the answer is that we have to be able to make a list out of them, and that list, naturally, we should disregard the order. So the list will not have an order, because we cannot have order for the set of rational numbers. But if we succeed to make a list of rational numbers, then we can start to count 1, 2, 3, 4, 5, and so on and so forth. So this will be a strategy. Think, contemplate, and apply. So that's what we are going to do. Okay, now I demonstrate the idea in general first. And then don't get scared, it's very elementary, the subject. Even grade school, 4, 5, grade school, they can comprehend it. And at the end I have some words to say about that. But I make it in general, then I make examples to make it more explicit and comprehensible. Okay, then in general, I select one of the intervals. The interval that I selected is AB. So I know that B will be A plus 1, whatever it is, one of the intervals I selected. Now in this interval, I start with 1 over B. That number always stays, that fraction always stays. 1 over B is 1 over the larger of the two consecutive integers, which is B. Then I write B over 1. I don't have to cross it, but B is already there because it's the end of the interval. But even if I do not erase it, let it stay, still I can come to the counting. I will come to back shortly after that. So I write 1 over B, then multiplicative inverse of that, which is B over 1. Then I'll go 2 over B, multiplicative inverse of that, which is B over 2. Then I'll go 3 over B, multiplicative inverse of that is B over 3. And so on and so forth, I continue until I reach B over B, which is 1. And 1 is already in the set, we will see that. Now the reason I said you don't have to cross B over 1, even to B over 1 is B and B is already there, and some other fractions, because if you can count from 1 to 10, you have already passed the counting from 1 to 7. So if the purpose is to count from 1 to 7, but you go to 1 to 10, you have already passed it and proved that yes, you can count them. So if we can have more fractions that we can count them, so definitely if there are few less, that means the set is countable. So that is as far as countability is concerned. But if our concern is about one-to-one correspondence, countable and one-to-one correspondence, then those fractions, those rational numbers that they have already been in the list in previous intervals, we do not repeat them. Then we have the one-to-one correspondence that we wish to have for the counting number. So I hope that you are clear with the general form, generic. Okay then, now let me make a specific example, 1 or 2 of them. Sorry for the primitive equipment I have, but the point is to convey the knowledge. Now, the intervals, first I start from 1 and 2, the interval 1 and 2. I partition the number line. Now in this interval, I start with 1 over B, which is the bigger of the two, the bigger of 1 and 2, which is 2. So I start with 1 over 2. The multiplicative inverse of that is 2 over 1. Is that right? It's 2 over 1, but 2 over 1 is the end point of that. I don't have to write it. And also 2 over 2, which is what? Which is 1, which is already here. So 1 over 2, 2 over 1, then 2 over 2, which is already here, so I don't have to write it. So 2 over 2 does not need to have to be here, 1 over 2, and 2 is here. So 1, 1 and a half, and 2. That's from first interval. Now I go to second interval. The second interval is the interval of 2 and 3. All right? Now, I start with 1 over 3. 1 over 3 always stays. Multiplicative of 1 over 3 is 3 over 1. But 3 over 1 is already the end point of the interval, which is 3. So I don't have to write it, I didn't write it. Again, if you write it, doesn't hurt as far as the countability is concerned, but it does hurt as far as the one-to-one correspondence with the counting number is concerned. Okay, now I go 1 over 3, 3 over 1, then 2 over 3. is 2 and 3 are, I come back also to this one, relatively prime. He ends up those numbers that they are relatively prime, numerator and denominator, they stay, and those that they are not relatively prime, which means they have a factor that divides both of them beside 1, then those usually are in the intervals before them. We will see that. So 1 over 3, 3 over 1. 2 over 3, which is proper fraction, 3 over 2, which is improper. Then goes 3 over 3, which is 1. 1 is already in the previous set, previous interval. Now another example. Let's go, instead of 3 to 4, let's go from 4 to 5, because 5 is a prime number. To see what? So I start with 1 over 5. Always 1 over b stays. No other interval, they have that number. The next one will be 5 over 1. But 5 over 1 is already the end of the word, the end of the interval. So I don't have to write it, that's what I circled it. I wrote it so that the algorithm, the procedure can follow. Then I go 2 over 5 next, and multiplicative on that, which is 5 over 2. Then I go 3 over 5, multiplicative inverse of that, which is 5 over 3. Proper and improper fractions next to each other. Then I go 4 over 5, then 5 over 4, then 5 over 5, which is 1. I circled it, and 1 is already in the interval before that. You follow me? So by doing that, I want to claim that the entire rational numbers will be in this set. There is no order. As we can see, 1/2 is here. Let's say some other one, 3/5, that should be, for example, here is already in another interval, the way I made it. So there is no order. But I can count them. Let's see how I can do that. No, I have one more that is, I don't know about zooming. I don't think I need to zoom it. I put it on, but you are good enough to see what's going on, so I don't really have to go to that deep. Now, I start with 0 and 1, then I go from 1 to 2, which is half, the only one stays. 2 over 1 is here, 2. Then I go from 2 to 3, that the fractions will be 1/3, 2/3, 3/2, and 3. I circle this. Then I go from 3 to 4, so that between 3 and 4, the fractions that are there will be 1/4, 3/4, and 4/3. And they are all relative to one another. Numerator and denominator are relatively prime to one another. Now, if they are not relatively prime, usually they are in the previous intervals that I'm making in the list but before. Now I can go from 4 to 5, and I already mentioned it, so that is the number. Then I can go from 5 to 6, that hopefully you can see that, and you can make it for yourself. From 6 to 7 and 7 to 8. Try to practice and see how you can say which one is there, which one is not. Okay then, now then the question comes is that you say, hey, all that you are saying is, you say positive, negative fraction. So what you are talking about is always positive fraction. So your list is only having positive fraction. What about negative? So answer is very quick, very easy. We are making a list. Just think, contemplate, reflect, and make discoveries. Here it is. Look at that. Next to every number that I made before in the intervals, put a negative, corresponding negative. That's simple. So 0, 1, then negative 1. Then 1/2, negative 1/2. 2, negative 2. So exactly same set as before we had, the same list that we have. By list I mean LIST, and just put the negative number between them. Isn't that interesting? Now comes the moment of the truth. The moment of the truth is to count them. Here it is simple. Count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on and so forth, and we go forever. So now the question is, what guarantee are you going to give to me that every rational number will be in this list? What guarantee can you give to me? Now, the guarantee I can give to you, I select one number in the previous the lecture that I'm going to use the same number. I select one number randomly, and I show that what interval that number will fall. So you can select any number you want, rational number, and you can show that what part of the list that number will fall. No order. One number, for example, is supposed to be between 1 and 2 and 3, end up to be 10 miles away in somewhere in the list. But it is in the list, that's the point. Now, in my lecture, one of my lecture, I did indicate that if a number that is given to you, because fractions are sometimes given as a over b integers, and sometimes are given in the decimal point, because our number is the base 10 place value. So if they are given in decimal form, then we have to convert them into a over b, where a and b are integer, a over b form, so that we can use this technique of possibly counting them. We put them in the list that we are interested. Are you with me? Okay. Now, how to convert a decimal point to an equivalent form of that into the form of a over b form, which a and b are integers. I have given a lecture about that. It's not complicated. Now I have this one, and this one I select a number randomly that end up to be 41.2222. And I want to know where this number will land in my list. First of all, I know ahead of the time that number will be what? Will be improper form, because is bigger than 1. So what I do, this procedure I have already given a lecture, how to convert that one into a over b. And when you convert it to a over b form, it ends up to be 371 over 9, which is 371 over 9 is equivalent, is same as 41.22222222, and so on and so forth, goes forever. So this is a over b form of it. This is decimal place value form of it, of the same number. They are equivalent. Now, the way that I did it in general, remember I started with 1 over b, which means the proper fraction will tell me what will be the two consecutive integers. So the number that I got was 371 over 9. So I know the multiplicative inverse of that should be in the list. The multiplicative inverse of this is 9 over 371. Is that right? Now, 9 over 371 indicates that the larger of the two consecutive integer is 371, the right one. And the left one should be what? 370. So the interval that I have partitioned the number line, the interval that I selected, this number will fall into the 370 to 371 interval. So I have guarantee any rational number you give to me, I can guarantee you will be in my list. So I succeeded to make a list of what? Of rational numbers, a list of rational numbers that now I can start to count them. 1, 2, 3, 4, 5, 6, and so on and so forth. So I can put them into one-to-one correspondence with the what? With the set of counting numbers. Now let's go back to the one I started with, and I said that intuitively and by common sense, we accept that since between any two rational numbers there should be another rational number, so that indicates that the entire number line should consist only of rational numbers. No other number can get the chance to be in the set of on the number line. So that is another one that our intuition fails us. That is another example that intuition is not trusted, number one, and intuition is limited. There are many things beyond the horizon that intuition will fail us to even think about them. But they exist and they are fact. Now, religion does go through this. Christianity and Islam, they say things that is possibly outside our comprehension, is counterintuitive, but the matter of faith makes it that 100% you agree and accept it. But some of them mathematically and scientifically we can prove it. Now, as an analogy, I also would like to say about one other one that is counterintuitive, about one of the aspects of theory of relativity. In the previous video lecture I did mention that, but I made a small, simple, innocent mistake. And I didn't want to go and make old video one more time, so I will correct it this time. Now, let me start and repeat the same experiment. Now, suppose I think this way will be good for you to see. Suppose that two cars of the same model are in the state of motion. One of them is ahead and is going 50 miles per hour. This one is behind and he comes going 100 miles per hour. So he comes and for a fraction of time, when the front bumper and rear bumper they align, then at that time it will start to go ahead. Well, they both are in the state of motion, don't forget. Goes ahead because it's going faster. So 1 hour later, this one is going to be 50 miles away from this, because this is already in the state of motion. Now, in case if this object was not in the state of motion, was standing still, so this subject that is going, this car that is going with 100 miles per hour, he comes and passes from that, and 1 hour later will be 100 miles away from this place, from this car. Common sense, huh? Intuition. Now, look, the counterintuitive will be the theory of relativity that almost all physicists, they agree and accept it. And let's see what he says. He says that this object, this one, the blue one, is going very, very fast, but not to the speed of light, maybe a little less. Now this object is going with the speed of light. Huh? Then he comes and passes from that. Of course, there is a moment that parallel to that. He comes and passes from that, and 1 second later will be 3 times 10 to the 8 meter ahead of this. Meaning what? Meaning regardless of the speed of this, whether this was in the motion or whether this was not in the motion, for the object that is going with the speed of light does not make any difference. So if he was standing still, he was 1 second later, he was 3 times 10 to the 8 meter ahead of it, which is the speed of light. And if it is still in the motion, that you are expecting the distance to be less, but the distance is still same, 3 times 10 to the 8 meter. Now the reason I brought this analogy is about intuitive and something that looks counterintuitive. Some of them, of course this is a theory, I don't think we ever get the opportunity to examine it, but many physicists accept it. Are you with me? And now going back to the real numbers, to the numbers that I said between two rational numbers, there is no other numbers, and it ends up to be not only number line has other numbers that in general we call them not rational or irrational, because irrational numbers also have different kind of irrational numbers. But in general we call them irrational, and the number of them is much, much, much more than rational. Interesting, isn't it? The rational number are supposed to fill up whole entire number line, and here we have other kind of number that we call it irrational, and the number of them are much, much, much more, infinitely more in fact. And the set of irrational number is not countable. You see how many there are that we cannot even count them. So since the real number is a union of rational and irrational, that means the irrational number should be uncountable. Because if the irrational number were also countable, then the union of them would have been countable with the same strategy that we used. Now, this subject is elementary. At grade school 5, 6, 4, they can comprehend it, and also junior high school. So if you have younger brother or sister, younger children in the grade school, late grade school, or junior high school, please try to discuss this kind of subject with them. And the advantage is that improves their critical thinking, improves their analytical thinking. So they can see that beyond the horizon, there are other things that they are counterintuitive. It may not make sense, but they are reality, they are fact. And I repeat myself, religion also goes into them, but that is the subject of theology. Some of them science and mathematics, in fact, proves them. Okay, then I thank you very much for watching. And as far as the real numbers not to be countable, we have also analytical proof for that. One of them is between negative pi over 2 and pi over 2, and using the tangent, if you know a little bit familiar with trigonometry. There are another one, you can use unit circle and have a semi-unit circle. There are other ways, analytical and geometrically, prove that the set of real numbers is not countable. Very interesting. But this is the beauty and flavor of mathematics. Okay, then I thank you very much. And as usual, I wish you all prosperity. And please stay safe. So long.